Hi again, everyone. Chris Tisdell here again. Thanks for tuning in. In this presentation, I'm going to continue my series of videos on mathematical research. And in this video, the title is Existence and A priori bound results for solutions to boundary value problems for fractional differential equations. Now, that's a very long title, but essentially, I'm going to concentrate on answering the question, when are solutions to fractional differential equations, when are the solutions bounded? Okay, that's pretty much it in a nutshell. Now, the presentation is a snapshot of a forthcoming research paper of mine in the Electronic Journal of Differential Equations, and I'll put a link in the description to that article when it's published. Okay. All right, so fractional differential equations are quite amazing. They're hundreds of years old, but they still have a lot of open questions regarding their solutions. Now, for fractional differential equations, in calculus, you think you have the first derivative, the second derivative. Well, what about a half derivative? What does that even mean? Well, this is how we define the so-called fractional derivative or fractional differential operator of order q, where q is between 0 and 1. Here it is. Here you can see you've got a regular derivative and an integral here. And based on that, the problem that we're going to discuss in this presentation is this system here. Okay, so we're keeping q between 0 and 1. You've got the derivative here. This is sometimes called the Caputo derivative because it's got this extra bit in it. You've got some nonlinear, continuous, vector-valued function f on the right-hand side. Big M and big N are matrices with constant components. And B here is a constant vector. So this is known as a fractional boundary value problem because you know something about the solutions at the endpoints at t equals 0 and t equals little a. Okay, so the question that this video is going to concentrate on is, suppose we're given something like this. How do we know that the solutions are bounded? Okay, so we're going to develop some sufficient conditions on F and the matrix M and the matrix N such that all solutions to this problem are bounded. So that's good because it gives you some sort of geometric understanding about the solutions and a location for potential solutions. Now, usually these kinds of problems are too hard to solve explicitly, so we try to get as much information as we can. Okay, so here are the research questions, if you like. What are sufficient conditions under which the original problem will have bounds on its solution? And a secondary question, and this is developed in the paper, is what are sufficient conditions under which two will have at least one solution? So it's like an existence problem. Now, once you have this kind of comes along for the ride. So the a priori bound results are the most important here. And that's what I'll be concentrating on. Okay, so a little bit of housekeeping first. There's an old saying that there are no differential equations, there are only integral equations, because usually when you're analyzing differential equations, you go to an integral problem, an equivalent integral problem. So you could say that there are no fractional differential equations, there are only fractional integral equations. And this is a theorem that links equation 1 and 2, this problem, with an equivalent integral problem. So what that means is that if x solves equation 3, then x solves 1 and 2. And if x solves 1 and 2, then it solves 1 and 3. If x solves 1 and 2, then it solves equation 3. Okay? So we're going to concentrate on this using this equation here rather than equation 1 and 2. And whatever we can do for this problem, that'll translate over to information about the solutions to 1 and 2. Okay, now I'm not going to prove that. The proof is in the paper, but we're going to apply this in the main result. Okay, so here it is. So this is our main result now. So let me see if I can squeeze that in there. All right, so we present our main result. Okay, by the way, in here you can see why this has to be invertible, because you've got the inverses here. All right. Okay, so let's just go through this. Suppose our F is continuous. Let the matrices M and M plus N be invertible. If you have some non-negative constants beta and L such that F satisfies inequality 4 everywhere, and then M and N satisfy this kind of inequality 5, so two inequalities there, then all solutions to the boundary value problem satisfy the following bound, okay, or a priori bound. Okay, you can see in here you've got the gamma function, you've got L, you've got beta, you've got the norm of these expressions. Now, the norm of the matrix here is any compatible norm with, say, the Euclidean norm for vectors. Okay, all right. So this is an important result. It looks very abstract. I've crammed a lot of stuff in there, but let's go through the proof and see how we go. Right, so we're looking for this. So we're going to use this. We're going to use this. We're going to use these things. Every assumption in the proof, in the theorem, we will use. Okay. So let's do the proof. Okay, so proof. All right. So let's let x be a solution to our original problem, and we're going to define a Lyapunov function by looking at the square of the norm of x of t. Okay. Now, there's a lemma from this paper here, which is a fantastic lemma, that gives you an inequality that relates the Caputo derivative of r with the derivative, the Caputo derivative of x. That is a really cool and important inequality, and you can do lots with it. And here it is here. Now, if x is a solution to our original problem, we can replace this with f, because these two things are equal in our differential equation, our fractional differential equation. Okay, so from our earlier theorem, we know that the problem 3 is equivalent to our original problem. This is the problem we're actually going to work with. Okay, so if we just move the m plus n inverse b over to the other side and take the norms of both sides, we get the following. Okay, so I've taken the norms, I've then put the norms inside to work on the f. These things are all positive. And I'm going to, and I've replaced it with an inequality sign. And now I'm going to work with this. Now I can replace this and this with the assumption in our theorem that is inequality 4. So I'm going to replace these things with that. Okay, so that and that are going to get replaced. Okay, so it's a bit of a mess now, but I've replaced there and there. And this has gone to there. Okay. And now what I'm going to do is relate this back to the derivative of something. So essentially, I'm going to have expressions here where you've got the fractional integral of a derivative, and you can apply a fundamental theorem of calculus. That's a really important point here. Okay, so that's what I've done. Okay, and then you get down to something like this. Okay, I know it's quite there's a lot of stuff happening here. So that's a ds over there. So if you continue down, you get these expressions here, where now, and I haven't defined this, but you actually have the fractional integral of a fractional derivative. So they cancel each other out, okay? All right, so I've got that on the last page. So the fundamental theorem of fractional calculus means that the IQ and the DQ cancel each other out. You end up with something like this. Remember, R of t is just the norm of x squared. And then the last step is that you can use the boundary conditions, okay, to form some more inequalities here. So that's what I've done, right? So that will disappear because it's non-positive, right? So that'll disappear. That's what's happened here. I've now written r of 0 in terms of x of 0. Same over here. And combining these, I can just rearrange the boundary conditions in my original problem, and I can get something that's negative here, or non-positive if you like. Okay, so that means it'll disappear. All right, so there I have used, on this page, I have used 5. Okay, inequality 5. All right, so if you look closely, this and this is exactly the result here, or the conclusion. Okay. All right, so when I was doing that proof originally, I was thinking, first of all, can I get a situation where I can apply some fundamental theorem? So I wanted to get the derivative and the integral in the one line so they could cancel each other out. Okay, now once you have a result like Theorem 2, the existence of solutions to the original problem kind of follows pretty simply. So under the conditions of Theorem 2, I can go a little bit further. I can say not only is there an a priori bound, but it turns out that 1 and 2 has a solution, at least one solution, and it lies in this zone here. Now the results for this these problems are new even in the scalar valued case. So when n equals 1 here, the results are still new, and you would sort of change these to just normal multiplication rather than here I'm talking about just a dot product, okay, in Rn, just the usual Euclidean one. All right, so there's lots of ways where you can tweak the results. If the beta was 0, then you would have f being uniformly bounded, and then you get more results there. So that's a classically important result. But if you want more, you can go and click on the paper, which I'll put the link to in the description when it is published. Okay, so I really enjoy talking about my research. I hope you can download the paper when it's ready. It'll be completely free. If you have any questions, any comments, I would love to hear them. Just put them in the comment section below. Thanks, everyone. See you later. Bye.